Hello everyone, this is Nikhila Tippannawar from Arihant College of Arts, Commerce and Science. Today we are going to learn trends in atomic properties of first transition series. We are going to learn about atomic and ionic radii, ionization enthalpy value and metallic character. Let's revise what is meant by atomic radii first. The atomic radii of an element is a measure of the size of its atoms, usually the mean or typical distance from the center of the nucleus to the boundary of the surrounding shells of electron. It can also be defined as one half of the distance between the nuclei of identical atoms that are bonded together. What is meant by ionic radii? It is the measure of an atoms in a crystal lattice. It is the one half of the distance between two ions that are barely touching each other. In an anion, it has an additional electron, which increases the size of an electron cloud and makes the ionic radius larger than atomic radius. And in case of cations, electrons is removed and the remaining electrons slightly held by the nucleus, resulting in a decrease in ionic radii than the atomic radii. Let's see the trends in atomic radii of d block elements. Atomic radii of the elements of transition series decreases gradually from left to right. As we move across the transition series from left to right, the nuclear charge increases by 1 unit at a time. The last field electron enters a penultimate n-1d subshell. However, d orbitals in an atom are less penetrating or more diffused, and therefore d electrons offer smaller screening effect. The result is that effective nuclear charge also increases as the atomic number increases along a transition series. From the table, we can observe that atomic size of the elements of 3D series gradually decreases up to chromium and then remains almost constant for a few more elements and then increases slightly towards the end of the series. We may observe that in 3D series, the decrease in atomic radii is small and it takes place from scandium to chromium. Then it remains practically constant up to copper and then increases. In the beginning, with increase in atomic number, the nuclear charge also increases. Still, the effective nuclear charge increases slightly as the added electron enters penultimate d orbital and increases the screening effect slightly from scandium to chromium. In the middle of the series, with increase in the number of d electrons, the increase in the nuclear charge and increase in the screening effect balance each other, and this leads to constancy in the atomic radii. And moving towards the end of the series, when electron pairing takes place in more and more of the d orbitals, the repulsive interaction between the added electron in each orbital is more than the attractive force due to the increase in the nuclear charge. Hence, the orbitals slightly expand and atomic radii marginally increases. Now let's see the trend in ionic radii. Ionic radii of transition elements show the same trend as of atomic radii. Why it is so? The elements of first transition series show variable oxidation states. The trends in ionic radii thus can be studied with elements having same oxidation state. With an increase of nuclear charge, a gradual decrease in ionic radii was observed. The trend is pronounced for the divalent ions of the first transition series. In general, ionic radii decreases with increase in oxidation state. For the same oxidation state, the ionic radii generally decreases with increase in the nuclear charge in given transition series. This trend is more pronounced for the divalent ions of the elements belonging to first transition series. As we can see, for chromium 2+ ion, the ionic radii is 82 picometer, and for copper 2 plus ion it is 72 picometer. Next, the oxidation states of the same element shows difference of 1 unit such as M plus ion, M2 plus ion, M3 plus ion, M4 plus ion, and so on. With higher oxidation state, the effective nuclear charge also increases, and hence decrease of ionic radii can be observed from M2 plus to M3 plus ion. Ionic radii of transition elements are smaller than ionic radii of representative elements of the same period. The ionic radii of a given element in the various oxidation state, if we compare, we observe that the ionic radii decreases with increase in oxidation state. This is due to increase of effective nuclear charge. Ionic radii of the transition elements are smaller than those of the representative elements of the same period. Next is ionization enthalpy. First, we will see what is meant by ionization enthalpy value. It is the amount of energy required to remove the most loosely bound electron from an isolated gaseous atom. The first ionization energy of the element A is the energy required by an atom to form A plus ions by removing first electron from its valence shell. In the same way, second ionization energy of the element A is the energy required by an atom to remove second electron from its valence shell to form A2 plus ions. It means a specific amount of energy is required to remove an electron from an atom. Look at the trend in first ionization enthalpies of d block elements. The ionization enthalpies of transition elements are intermediate between those of s block and p block elements. This suggests that transition elements are less electropositive than elements of group 1 and 2. Depending on the conditions, they form ionic or covalent bonds. Generally, in the lower oxidation state, these elements form ionic compounds, while in the higher oxidation states, they form covalent compounds. The first ionization enthalpy increases with increase in atomic number across a given transition series, although the increase is not very regular. The added electron enters into n-1 d subshell and shields the valence electron from the nucleus. Thus, the effect of increased nuclear charge is opposed by the screening effect of n-1 d electrons. Therefore, the increase in ionization enthalpy with increase in atomic number is rather slow and not very regular. The first ionization enthalpies of elements of third transition series are higher than those of the elements of first and second transition series. The atoms of elements of third transition series possesses faint 4f orbitals. 4f orbitals show poor shading effect on account of their peculiar diffuse shape. As a result, the valence electron experience greater nuclear attraction. A greater amount of energy is required to ionize elements of the third transition series. The ionization enthalpies of the elements of third transition series are therefore much higher than that of first and second series. Look at this table. The table represents ionization enthalpies of first transition series elements. Ionization enthalpy shows in table reveal that for a given element there is a substantial increase from the first ionization enthalpy value to the third ionization enthalpy value. And as we move across the transition series, slight variation is observed in the successive enthalpies, that is ionization enthalpy 1, second ionization enthalpy and third ionization enthalpy of these elements. Now we will see the metallic character. What is meant by metallic character? Metallic character describes the set of chemical properties associated with the elements or metals. Metallic character depends on the ability of an element to lose its outer valence electrons. Properties of metallic character include metallic luster, hardness, ductility, malleability.
As we have already learned, all the transition elements are metals and exhibit all the properties which are characteristics of metals. They are hard, lustrous, malleable, ductile, and possesses high tensile strength. They have high thermal and electrical conductivity. Their melting points and boiling points are quite high. Nearly all transition metals have the simple hexagonal closed pack HCP, cubic closed pack CCP, body centered cubic PCC lattice, which are characteristics of true metals. The metallic character of transition elements may be attributed to their low ionization enthalpies and the presence of several vacant orbitals in the outermost shell. This favors the formation of metallic bonds in them. Hence, they exhibit typical metallic properties. Low ionization enthalpies and vacant d orbitals in the outermost shell are responsible for the metallic character of the transition elements. This favors the formation of metallic bonds and thus these elements show typical metallic properties. The hard nature of these elements suggests the formation of covalent bonds in them. This is possible due to presence of unpaired n-1 d electrons in these elements. All the transition series elements, they have high melting points. The melting point steadily increases up to D5 configuration. Chromium, molybdenum and tungsten show highest melting points in their respective series. Manganese and technetium display anomalous values of melting points. After this, with increasing an atomic number, the melting point decreases regularly. Thank you everyone.